Hey guys, welcome back. We got redox reactions today in this video. Right, so an example of a redox reaction. You have zinc metal, copper 2 nitrate, going to zinc nitrate, and then copper metal. So one thing that does not change, right, and we'll kind of make it purple here, is nitrate. Nitrate just stays there. It's a spectator ion, right? So our oxidation states, you have zinc has 0, right? Because why is zinc 0? Well, if you look at zinc, how many protons does zinc have? Right? Zinc has 30 protons. And over here, we got 30 electrons. On the other side, right, zinc is zinc 2, still 30 protons, but now it only has 28 electrons. Oh, it didn't change color. Conversely, copper has 29, yep, it's 1, 4, 29 protons, 29 protons. But over here, copper 2 is 27 electrons. And copper metal is 29 electrons. All right, so copper goes from +2 or 2 plus to 0. And so we know these two reactions down here, these are our half reactions. All right, so you look at the oxidation half reaction, zinc going to zinc 2 plus 2 electrons. Right, and so what we mean by here is this zinc metal is going to zinc 2 plus and then given 2 electrons as well. The reduction, copper 2, right, gains these 2 electrons to go to copper metal. Now, we have a balanced chemical equation here, but in solution, you know that copper and nitrate break apart, and so does zinc and nitrate break apart, right? They're not there, right? They're floating around independently of each other. Okay, and so the electrons prefer to be on copper. All right, and so if we look at how we would do this, why we're kind of calling them half cells, is imagine you had a voltmeter. And so what we have is two systems here, right? Over here, we'd have a solution of, I'm using nitrate, so this would be CuNO3 2. And this would be ZnNO3 2. And I'd have something like, I don't know, a salt. My salt would be, let's say, NaNO3, sodium nitrate in there. That's a horrible 3. All right. And so that's salts in this salt bridge. If we were to have a voltage thing, with some electric clamps, I'd have, your alligator clamp on the zinc metal, and then it would go into the voltmeter. And then coming out, you'd have your clamp for copper. You would see that if we did this, we would have 1.10 volts. And we'll get to that in a few. All right. And so what's going on physically here? Let's going to zoom in this, all right? Let's define some terms here. So this is a voltaic, or some books call it galvanic cell, right? Which means it's spontaneous. What does that mean? That means it's going to happen without any outside intervention. As soon as these wires are connected to these two half cells, right? The voltmeter is gonna just read, all right? What does that mean? Okay. Well, let's define everything and then we'll talk about this. So on the left here, we have the anode, which is oxidation, right? And over here, we have the cathode, which is reduction. Now, electrodes. That would be an electrode. All right. This is also an electrode. All right. That's what those would be like zinc metal and copper metal, respectively. Okay, so what happens? If we come down to this solution right here, I have zinc metal on here, zinc 0 atom, and that's going to go into solution. No. It's going to come into zinc 2 plus in solution, right? And that means 2 electrons are going to go that way. All right, they're going to come up, and the electrons are going to keep going this way. They're going to go this way. Through the voltmeter. They keep coming this way. They keep coming this way. They go down the electrode. They keep coming down. The electrons keep coming down. Both of them coming down. And you're going to have Cu 2 plus in solution. And that's going to adhere to the surface and become Cu solid. And these electrons are going to go to that copper. That makes sense? So that's what was kind of happening. Now, positive charge is coming out of the solution. So I have extra nitrates in here now. So now we have 2 nitrates that do not have charge balance because the copper ion left. So that means in our salt bridge, what color did I use? Pink. Our salt bridge, I have sodium ions coming through, right? 2 of them, right? And so to complete this circuit, right, nitrates have to be coming in here to replace or to match up with the zinc. So that means the electrons start right here. All right, zinc goes in there, but the electrons start here. They go through and they go to here. The rest is charge, then is balanced with the salt bridge. Okay, so let's write that kind of out. All right, electrons flow from the anode to the cathode. Right? The salt bridge permits movement of ions to complete the circuit. Oh, that's horrible, though. All right, so that's what's going on. So, right, what's going on with these solutions? The concentration of Cu2 plus in this solution decreases with time, right? And your electrode goes from this, right, to something like that, right? Where it gets bigger with time, and not evenly. Conversely, our concentration of Zn2 plus here increases, and the anode, the zinc electrode, goes from this to something like this, where it becomes depleted. right? Something like that, right? Where it's depleted, if that makes sense. Okay, so that's basically what we happened. This is one of the first quote unquote batteries or cells chemists have actually studied, right? Okay, and so the question then, what is driving these electrons to go from zinc to copper? That's the question. All right, and I want to address that. Okay, so what's happening is electrons flow from the anode down the wire to the cathode. All right, salt bridge. Oh, we just did this. So the electrons have a higher potential at the anode. What does that mean? A higher potential at the anode. Potential to do what? Right. So when we think about potential energy, what do you think about? It's stored energy. All right. Okay. So if you're on the ground floor, if you're on the ground and you roll over, you're probably not going to fall. If you're on a bed and you roll over, you can fall off the bed. If you're up on the second bunk, let's say, and you roll over, you have more potential energy than on the first bunk, if that kind of makes sense to you, right? Like jumping out of a downstairs window is more doable than like a second story window or even a third story window. It gets kind of crazy, all right? And so if we look at this, it's kind of analogous to a water reservoir, all right? All this, how this works. Okay, so we measure this potential difference in volts. Maybe you've seen volts, right? I'm sure you have, right? That's the force that makes the electrons move, all right? So energy equals volts times coulombs. So let's define these things. So a volt, all right, a volt is equal to, right, a joule divided by C, coulomb. I can't even read that. All right, so what is this? This is energy divided by charge. So coulomb's a measure of charge, right? And if we break it down even more, a joule, what is a joule? Well, I like to break down. Joule is a Newton meter. What's a Newton? Right? A Newton is a kilogram mass times acceleration. Kilogram times meter per second squared. Right? So a joule is a kilogram times meter per second squared. Right? That's a joule. Coulombs are amps times seconds. It's called an amp times a second. So this breaks down ultimately into kilogram. Oh, I missed the meter squared. Meter squared, amps, second cubed. That's what a volt is. So one coulomb is the quantity of charge that passes a point in an electric current circuit when a current of 1 ampere flows for 1 second. All right. So an ampere, which is a rate, is equal to 1 coulomb over 1 second. Right? And coulombs equals amps times seconds. All right? So amps are rate. So if you think about wherever you guys live, you probably have a circuit breaker box now. Now, there are still some houses that have fuses. Cars have fuses, boats have fuses. Sometimes they have breakers now. But a circuit breaker is like a 10 amp, 15 amp, 20 amp, whatever the ampere is on the circuit. That's a little number on the circuit breaker. That's how many amps can go through that circuit before the breaker trips, right? Because as you guys know, probably, the resistance is in the wires, and resistance causes heat, and if it gets too hot, we don't want the wire or whatever we're using to catch fire, because it's very bad inside a house, right? We don't want to have fires in the house unless you have a fireplace, and that's the only place you want the fire in your house, probably, unless you have a candle that's a controlled fire, right? And so we don't want electrical fires. And so that's what amps are. Amps are rate. Coulomb is an amount of charge. So we know charge on an electron is 1.602 times 10 to negative 19 coulombs. All right, 1 mole of electrons equals 96,485 coulombs. So if you have a mole of electrons, that's what you have is charge-wise. And then 1 amp is equal to 6.241 times 10 to the 10th electrons. All right? Wow. Okay. So now when we talk about this, volts is energy per charge, and we want to get some work out of this, all right? And so we have some things here. Delta G equals negative NFE. I just threw this in there, right? The maximum non-expansion work, right? Delta G, right? So negative N. What is N? N would be our moles of electrons transferred. F, that's our 96,485 coulombs per mole of electron. And E, this is our standard reduction potential. All right, we're going to talk about that later on, all right, in a little bit. We'll talk about that in a little bit, okay? But when we talk about what's driving these electrons to go forward, all right, think about as you have this water up here, and for the water to come down, right, we do this. This is how dams work, right? And there's, a dam, there's a turbine in here, right, that you're turning to spin to make the electricity. But it's just in general, all right, there's a couple things here I want to talk about. The potential difference is how high it is, okay? So that's the voltage. That's the voltage. And so if you imagine if this extended down and you could walk right here, and this was just straight down like it was a waterfall. And you could just walk, right? It doesn't matter if it's a waterfall, whatever. The height of the waterfall would be the voltage, okay? And so in order to cross this, let's say you could cross this. If you're on, I don't know, a walkway, not a big deal, all right? If you had a waterfall, all right, let's say you had a waterfall. I'm going to draw a side-on picture here, all right? And let's say this is, all right, we'll give it different feet. So there's our water coming, right? Our water is just coming over our waterfall, right? Okay. If that's you, right? And this is 10,000 feet, okay? But that distance was, let's say, 1 foot. You would cross that stream no problem. That would not be a big deal. That makes sense, right? Like, just step over it and go. Not a big deal, right? You can be on the edge. As long as the footing's good, not a big deal. Now, if we change this so that .5 feet, half a foot drop, but this is, I don't know, 10 feet wide and 10 feet deep, and it's moving fast, all of a sudden it's a different story, right? A fast-moving river that has very little slope is way more dangerous than a little tiny river with a lot of slope, if that makes sense, right? And so when we think about voltage, voltage is the potential difference. The current is how much of this water is coming down, right? Okay, that's the amps. How much coming down, right? And so when we think about what's dangerous, ampere is more dangerous than the voltage. The voltage is the potential for it to move, right? Current's what's actually moving, okay? And so when we look at what this works, energy is joules, right? And so I'll get my, all right? So all the joules. And so let's talk about this. Volts times amps times seconds is a joule, all right? Volts times amps are watts. Because watts are joules per second. Volts are joules per coulomb. Amps are coulombs per second. Coulombs, right? Seconds. Okay? And so amps times seconds is a coulomb. All right? So if you have an amp times a second here, that's a coulomb. All right? So that's kind of how it breaks down. So that's the energy. Now, in the next video, we're going to look at these reactions, and we're going to talk about this. All right? So hopefully there are questions, and you watch the next video. But if there's any questions that are not clear, feel free to reach out. Otherwise, we'll see you next time.